Okay, welcome everybody to physical science today. Yes, everything you said was right. Keep talking, I appreciate that. So you saw those three examples of Bernoulli's principle. And as the velocity of a fluid increases, the pressure exerted by the fluid decreases. Okay. So I'd like to show you the physics behind that. So you guys remember talking about 6.02 times 10 to the 23rd? Yes. And that's how many particles are in that box? Right? And my question to you is then, which way is the average direction of the movement of the particles? Basically all directions, right? So if we have gas, okay, it's going to go out of the board, into the board, up, down, sideways, all these different directions is the movement of the particles, right? And so that pressure thing is these particles forcing or hitting stuff. And so you sum up a whole bunch of little forces from little tiny collisions, and then you get pressure. Air pressure is what we're talking about right now. So what happens then, we're going to just say that these are the cans. I'll draw, well, we'll say that this is the top of the cans. So here's the top of the can, and you have your tab here, right? Does that look kind of like the top of a pop can? Yeah. And here's the other top of the pop can, and you got a little tab in there. So all these particles are moving all these different ways and hitting those cans. Okay, so what happens when you blow? What happens now? The particles right outside of your mouth. The particles right outside of your mouth. So once you blow, you're taking this gas particle and ramming it into a gas particle that might be going this way, right? What happens when I ram a particle even faster?
You push it.
It starts changing direction. It might go that way instead of that way, right? And then the next one, and pretty soon I have all these particles hitting all these other particles, and then we get basically a particle flow that's called laminar. L-A-M-I-N-A-R. Have you heard of laminate wood? It's layers, right? So when we have laminar flow, and that's L-A-M-I-N-A-R, laminar flow, then what happens is that constant random motion becomes less random, and the particles then start ending up, instead of them going in all directions, this one gets hit and starts going that way. Do you see what I'm saying? And so now most of the particles in this little area are going in one direction. And this whole idea of pressure is because these particles are going in almost all directions at all times, and they're forcing in almost all directions at all times. But when I start getting this laminar flow, then the net force becomes much greater in this direction. Now, does that suck them together? Well, not necessarily by itself. But what's happening out here? The pressure out here is still, well, the fluid is still not laminar out here because I'm not blowing in that part. So now there's less pressure or less force that way than there is this way. So then the can moves towards the lower pressure. Does that make sense? Partially? Okay, what you have to know, this is the explanation of the physics behind this Bernoulli's principle. This is why it works. But the words that you have to know for the test then are going to be, as the velocity of a fluid increases, the pressure exerted by the fluid decreases. It's kind of a small part of the whole picture. Okay, but that is what you'll have to know at this level. So this is one of the principles of flight in an atmosphere. Now this doesn't work out in space because there's no air out there. So there's no pressure out there. But like an airplane flight, so this is kind of basically the way a wing looks like, right? Do you guys agree with that? Have you ever karate chopped a big chunk of Jello?
Yeah.
Well, imagine doing it. Like a big chunk of Jello. What happened? Well, last time I did it, this is what the big chunk of Jello looked like, and I put my little hand through there. I mean, it was really big at the Science Center. And what ended up happening is my hand was kind of like the Jello split here, but then what happened to it? It came back together, right? So every time you try to chop a big piece of Jello, it splits and comes back together. That's the same thing, kind of. That's kind of the same thing with pieces of air. See that? So you got two pieces of air, they kind of come back together, like you're splitting it. So what happens? Look at this. Look what happens here. In the end, which one has to travel further? Which one travels further, the top or the bottom? The top. So that means it's going faster, which increases its laminar flow, which does what? Decreases the pressure. So I have lower pressure here, higher pressure here. The net force then, because force over area is pressure, is upward, and that's what causes the wing to lift because of the shape. Now there's other factors in play too. And this doesn't work at all in space, because there's no Jello in space. Okay, there's no Jello in space. Although there is Jello in the spaceship.
Is there really?
Well, there's air in the spaceship, yeah. Okay, and there might be Jello. Okay, thermal expansion, then. Thermal expansion we've talked about maybe about 3 times, right? Haven't we talked about thermal expansion about 3 times? So you already know about that quite a bit. Okay. Okay, so thermal expansion. We've already talked about that. If we add heat to something, it expands. Do you agree? Okay. And as it gets cooler, it contracts. These characteristics are called thermal expansion. Viscosity increases as temp decreases. Why do you think that is? Yeah, so the viscosity increases because viscosity is resistance to flow. And so as something gets colder, the particles get closer together and they get a little more rigid, a little more thick. And so, because they're moving less. So what happens when I throw heat on a crowd? They move more, they need more energy, right? So if I take heat away, then it moves less, it needs less space. I said need more energy, I meant need more space. So now we finally get to gas laws, okay? So all of this stuff we talked about is going to be expressed in these laws. But Boyle's law is the volume of a dry gas is inversely proportional to the pressure provided, to the pressure, period, provided the temperature remains constant. Okay? Okay, so I gave you 2 plungers, and you guys said that there's air in here, right? And the air is constant because these plungers aren't letting any more in or out, and they're connected with this rubber tubing. And what's happening to these particles in here? They're moving in all directions. Do you agree?
Yeah.
Okay, so the question is, when you push this plunger that direction, you guys all felt it getting, it's putting on more force. More and more force, it's harder and harder to push. So if we're talking pressure, it's force per area, and area is just this circle, right? Why, due to the kinetic theory, is the pressure increasing? So the right answer is, you decrease, so when your plunger is here, you decrease the volume that these particles have to move around in. Now, temperature is the average speed, right? Have you increased the temperature? Well, not really. But they don't have to travel as far before they hit the next particle. So you're increasing the number of times that you hit something, therefore increasing the number of times you're forcing on area.
Doesn't the temperature increase a little bit?
No. So tomorrow we will talk about doing math with Boyle's law.
No.